Welcome back to the A+ Tutor. Today we're going over how to simplify and verify expressions using your trig identities. Trigonomic identities are used to simplify complex expression. There are different types of trig identities that can be used to simplify these complex expressions. Now keep in mind our trig functions are sine, cosine, and tangent. Let's go over what some of these identities are, starting off with our reciprocal identities. So, we know we have sine, cosine, and tangent. Well, sine is equal to 1 over cosecant. That's our reciprocal of cosecant gives us sine. Cosine is equal to 1 over secant, or our reciprocal of secant gives us cosine. And tangent is equal to 1 over cotangent, and vice versa. So this also means that cosecant is equal to the reciprocal of sine. Secant is equal to our reciprocal of cosine, and cotangent is equal to our reciprocal of tangent. On top of that, we have our quotient identities that we use specifically with tangent and cotangent because we know tangent can be written as sine over cosine. And if cotangent is our reciprocal of tangent, then cotangent is equal to cosine over sine. So when we get into expressions like simplify sine x times cotangent x or things like that, we want to start to use some of these identities in order to be able to simplify these functions. So we defined our trig functions, our reciprocal identities, and our quotient identities. And now let's go over our Pythagorean identities. So if we remember our unit circle, the radius of our unit circle is 1, which means if we have a triangle, our hypotenuse will be 1 because the radius of our unit circle is 1. Here's our theta, or our angle. And then our horizontal line is our x-axis, our vertical line is our y-axis. Let's recall our Pythagorean theorem, which is a squared plus b squared equals c squared when we have a right triangle. So if we use Pythagorean theorem with this triangle, we know that x squared plus y squared equals 1 squared. Now, if we remember with our trig functions, our SOHCAHTOA, or how we can find our sine, cosine, and tangent of our angles using our side measurement, we know our sine is opposite over hypotenuse, our cosine is adjacent over hypotenuse, and our tangent is opposite over adjacent. So for this triangle, our sine of theta is equal to our opposite, which is y, over our hypotenuse, which is 1, or just y. Our cosine of theta is equal to our adjacent, which is x, over our hypotenuse, which is 1, or just x. So if we know our y and x, we can plug these back into our Pythagorean theorem, or our expression for our triangle, because, again, we found our x and y. So that means our x is cosine, and our y is sine, equals 1. Or cos squared theta plus sine squared theta is equal to 1. Now, usually you're going to see this written as sine squared theta plus cosine squared theta equals 1. And that is our Pythagorean identity. Now, there are two more that go along with this, because as we saw with our reciprocal identities, we can take the reciprocal of all of our functions to give us a different function. So if we have sine squared theta plus cosine squared theta equals 1, and if we divide everything by sine squared theta, then we would get sine squared over sine squared is 1. Cosine squared theta over sine squared theta is the same as cosine over sine, which is our quotient identity of cotangent. So we know that cotangent is cosine over sine, which means cosine squared theta over sine squared theta is cotangent squared theta. And 1 over sine squared theta, our reciprocal identity, tells us that's cosecant. So this is cosecant squared theta. And now that's another version of our Pythagorean identity. We have sine squared plus cosine squared equals 1. We also have 1 plus cotangent squared equals cosecant squared. So if we divided everything by sine, let's divide everything by cosine. So we'll divide sine by cosine, cosine by cosine, and 1 by cosine. Sine squared over cosine squared is going to be our tangent squared because sine over cosine is tangent. So sine squared over cosine squared is tangent squared. Cosine squared over cosine squared is 1. And 1 over cosine squared is secant squared. And there's our last version of our Pythagorean identity. So we may find ourselves in these equations with some version of sine squared, cosine squared, cotangent squared, cosecant squared, all of these different things. And now we've identified these Pythagorean identities that will be able to help us simplify those expressions. And the last set of identities we'll go over for this video will be our even-odd identities. Basically, for odd functions, we know that f of the opposite of x is equal to the opposite of f of x for all x in f. For even functions, f of the opposite of x is equal to f of x for all x in f. So when we think about our odd functions, those are our lines or our cubic functions, and even functions are things like parabolas, where we take a value on the left and it gives us the opposite value on the right side of our equation. So that's how we can identify our even and odd functions, and let's see what these are when we think about our trig functions. Where do we have an even function and where do we have an odd function? So if we think about this in the context of our trig functions, let's start with sine. What is the value of sine of the opposite of theta? Let's say theta is equal to pi over 2. Let's think about the graph of sine. The sine graph looks like this, where we have our pi over 2 value here, and this is our negative pi over 2. Well, sine of pi over 2 would be right here and is a positive 1. And sine of negative pi over 2 is down here, which is a negative 1 value. Which means that sine is an odd function, and we can generalize this and say that the sine of negative theta is equal to the negative sine of theta. So let's look at our cosine then. What happens with cosine? Let's take theta equal to pi. Let's consider our theta is pi. Well, again, if we think about the graph of cosine, let's take our pi value. So we've got our pi here, positive pi, and our value for cosine is negative 1. So cosine of pi is equal to negative 1. Then when we go to the opposite side of our negative pi value, our value for cosine is still negative 1. So cosine of negative pi is equal to negative 1. Therefore, our cosine of negative theta is equal to the cosine of theta. And cosine is an even function. So then what does this mean for the tangent of negative theta? Well, tangent is equal to sine over cosine. So the tangent of negative theta is going to be equal to the sine of negative theta over cosine of negative theta. And we just saw that the sine of negative theta is negative sine theta, and the cosine of negative theta is positive cosine theta. So negative over positive means that tangent of negative theta is equal to the negative tangent of theta. Then we have our reciprocal identities. So we have to now figure out what our cosecant, secant, and cotangent are. Since we just found our sine, cosine, and tangent, we'll be able to solve for these pretty easily. So we know that cosecant theta is equal to 1 over sine theta. This means that the cosecant of negative theta will be equal to 1 over the sine of negative theta. And we know the sine of negative theta is negative sine theta, which means cosecant of negative theta is equal to negative cosecant theta. Similarly for secant, what is the secant of negative theta? Well, secant theta is equal to 1 over cosine theta. So secant of negative theta would be equal to 1 over the cosine of negative theta, which is equal to 1 over cosine theta. So secant of negative theta is equal to the secant of theta, just like our cosine. And for our cotangent, we know that cotangent is equal to 1 over tangent. So cotangent of negative theta would be equal to 1 over the tangent of negative theta, which is equal to 1 over the negative tangent. So cotangent of negative theta is equal to negative cotangent theta. Now let's go into some examples of simplifying expressions using all of these trig identities that we just learned. Starting us off, we have sine theta secant theta. So remember, secant theta is 1 over cosine theta. So that means we can rewrite this as sine theta times 1 over cosine theta, which then can be written as sine theta over cosine theta. And if we remember our reciprocal identities, that means this is equal to tangent of theta. And we've simplified this. So whenever we are simplifying our trig expression, we want to get it to the simplest form possible, usually only involving one trig function. Next we have secant x over cosecant x. So we know that secant x is 1 over cosine and cosecant x is 1 over sine. So if we do our kind of keep, change, flip, or if we divide these fractions, we would have 1 over cosine, so we keep the top of our fraction, change our division and multiplication, and then flip or take the reciprocal of our bottom fraction. So then this gives us sine x over cosine x, which looking at our quotient identities is tangent x. And that's our answer. Number 3, our third example is cosine squared x times 1 plus tangent squared x. So we'll leave our cosine squared x alone. There's not really anything we can do to simplify that right now. But 1 plus tangent squared x we know is the same as tangent squared x plus 1. 1 plus tangent squared x is going to be secant squared x. We can write this as cosine squared x times secant squared x. And secant squared x can be rewritten as 1 over cosine squared x. So that means we have cosine squared x times 1 over cosine squared x. Those will cancel, and we're left with 1. So this simplifies to 1. Next we have cosecant x plus cosine x cotangent negative x. Let's rewrite everything we can rewrite. Cosecant x is 1 over sine x. Cotangent negative x, so if we look at our even odd identities, is going to be the negative cotangent of x, which can then be written as negative cosine x over sine x. So if we rewrite our expression, we'll have 1 over sine x plus cosine x times negative cosine x over sine x. This gives us 1 over sine x minus cosine squared x over sine x. These two have the same base, so we can subtract these. We can write this as 1 minus cosine squared x over sine x. And our numerator, 1 minus cosine squared x. So now if we take our Pythagorean identity and subtract cosine squared from both sides, we get sine squared equals 1 minus cos squared theta. So now we can put that in our numerator. We know that 1 minus cosine squared theta is sine squared x over sine. And that means we can simplify because we have sine squared on top and sine on the bottom. So that means this is equal to sine x. And that's the simplified form. So sometimes you do have to get a little creative with how you are rewriting your functions. You want to see what elements of your identities are present in whatever you have and what you're trying to simplify in that expression. So here we had to rewrite our Pythagorean identity, and you're going to see different versions of that as we do some more examples. Next, we have 1 plus tangent squared x over cosecant squared x plus sine squared x plus 1 over secant squared x. So let's go one by one. Let's start with our first fraction. We have 1 plus tangent squared x, and we know that tangent squared theta plus 1 is equal to secant squared theta. So this right here is secant squared x. So we can rewrite this as secant squared x over cosecant squared x. We can't do anything to our sine x right now, sine squared x, plus 1 over secant squared x. We see in our reciprocal identities that 1 over secant squared x, or secant x, is equal to cosine. So we can just rewrite this as cosine squared x. So now secant is 1 over cosine, and cosecant is 1 over sine. So we'll rewrite this expression here to 1 over cos squared x over 1 over sine squared x. And then sine squared x plus cosine squared x is equal to 1. So we'll add 1. Now if we take this fraction and we do our keep change flip, we have 1 over cos squared x times sine squared x over 1, which is sine squared x over cos squared x, which is tangent. So we can rewrite this as tangent squared x plus 1. And tangent squared x plus 1 is secant squared. So that means this simplifies to secant squared x. Here's our last example for this section. 3 sine cubed x cosecant x plus cosine squared x plus 2 cosine negative x cosine x. So starting us off, we know that cosecant is 1 over sine. So in this first part of our expression, 3 sine cubed x times 1 over sine x, we can start to simplify this because 1 over sine will get rid of one of our sines in the numerator, and we're left with 3 sine squared x. Our cosine squared x we can't do anything with right now. For our cosine negative x, we know that cosine negative x is equal to cosine x. So this becomes 2 times cosine x times cosine x, which can then be simplified to cosine squared x. So when we rewrite this now, we'll have 3 sine squared x plus cos squared x plus 2 cos squared x. Well, these can be combined, our cos squared x and 2 cos squared x, because they are the same cosine. We're using cosine squared. So we can write this as 3 sine squared x plus 3 cosine squared x. If we factor out a 3, we're left with sine squared x plus cosine squared x. And we know that that is equal to 1. So this is 3 times 1, or 3. So our entire expression simplifies to the value 3. For this next set of examples, we're going to verify our trig identities. We're going to be presented with an expression, and we want to use our identities to make one side look like the other. So if we have tangent theta plus cotangent theta equals secant theta times cosecant theta. So we need to use our identities to make one side of this expression look like the other. When we are doing these, we're either going to pick to work with just the left side or just the right side. Sometimes you can kind of see which side you should work with, which is going to be the better option for you in order to get yourself to the other side of that expression. So for this expression, let's work with the left side of our expression. Tangent, as we know, is sine over cosine. And then cotangent is the reciprocal of that, cosine over sine. So we can rewrite tangent as sine over cosine plus our cotangent, which is cosine over sine. Now from here, what we want to do is we want to be able to combine this fraction. So the way that we're going to do that is we need a common denominator. Our common denominator is going to be sine times cosine. So we're going to multiply our first fraction by sine over sine. We're going to multiply our second fraction by cosine over cosine. Our first fraction becomes sine squared theta over sine theta cos theta. Our second fraction becomes cos squared theta over sine theta cos theta. So now we can bring these two fractions together and we get sine squared theta plus cosine squared theta over sine theta cos theta. Now this, as we know from our Pythagorean identities, is equal to 1. So we'll write this as 1 over sine theta cos theta. Our goal is to make this look like secant theta times cosecant theta. So we'll want to break this fraction up and write this as 1 over sine theta times 1 over cosine theta. Because we're connected by multiplication in our denominator, we are able to do this. 1 over sine theta is cosecant theta, and 1 over cosine theta is secant theta. So that means this is equal to cosecant theta times secant theta, which is exactly what we're looking for. And we verified this identity. So we're going to work with one side of our expression, simplify that, and use our identities to get this to look like the other side of our expression. For our next expression, we have cosine x minus cosine cubed x equals cosine x sine squared x. Let's start on our left side by factoring out a cosine x. When we factor out a cos x, we're left with 1 minus cos squared x. And we know that 1 is equal to sine squared x plus cos squared x. So we can rewrite this as cos x times sine squared x plus cosine squared x minus cosine squared x, which means our cosines will cancel, and we're left with cosine x times sine squared x, which is exactly what we were looking for, and we verified our expression. Now, something I do want to point out is there is not always one way to get to the answer. It's important to make sure we're using our identities and pulling out what is relevant for that expression based on the trig functions that we see. But sometimes you can use different identities to get to the same answer. For our next expression, we have 1 plus sine x equals cosine squared x over 1 minus sine x. So again, let's work with the left side of our expression. And something that we can do is, based on what it looks like on the right side, we can decide what we want to do on the left side. So on the left side, we have 1 plus sine x. And I do want that fraction. I want to get this over 1 minus sine x. So what I can do is I can multiply this by 1 minus sine x over 1 minus sine x. If I multiply this by a fraction that equals 1, I'm not changing the value of my expression at all. So since 1 over sine x over 1 over sine x is equal to 1, I can multiply that by my expression that I have on the left side. So this is equal to 1 plus sine x times 1 minus sine x in our numerator, all over 1 minus sine x. If we FOIL our numerator, we get 1 minus sine squared x over 1 minus sine x. Now, Now we know 1 is equal to sine squared x plus cosine squared x. So we can rewrite our numerator as sine squared x plus cosine squared x minus sine squared x all over 1 minus sine x. Now sine squared x minus sine squared x will cancel. So that means we're left with cosine squared x over 1 minus sine x, and that's exactly what we were looking for, and so we verified this expression. Next we have cosecant theta minus cotangent theta over secant theta minus 1 equals cotangent theta. So usually when we're looking at these expressions, I find it's easier to work with the side that has more options, more of the trig expressions or trig functions, because you're going to be able to do more simplifying with that and rearranging and changing. So if we were just to look at cotangent, it'd be really difficult to get cotangent to look like the left side versus simplifying the left side to look like the right side. So we know cosecant is 1 over sine. Cotangent is cosine over sine. And secant is 1 over cosine. So let's rewrite all of those expressions. We get 1 over sine minus cosine over sine all over 1 over cosine minus 1. So our numerator, 1 over sine minus cosine over sine, can be grouped into one expression. So we can write that as 1 minus cosine all over sine. And in our denominator, 1 can be written as cosine over cosine. That's the same as 1. So we can write our denominator as 1 minus cosine over cosine. And if we do our keep, change, flip, we'll have our numerator, which is 1 minus cos theta all over sine theta, times, we'll flip our denominator, cos theta over 1 minus cos theta. So now our 1 minus cos thetas cancel, and we're left with cosine theta over sine theta, which, as we know from our quotient identities, that's equal to cotangent theta, which is exactly what we're looking for, and we've verified this expression. Our next expression is 1 plus sine x over cosine x plus cosine x over 1 plus sine x equals 2 times secant x. So again, we'll work with the left side of this expression. Let's start by working to combine these two fractions. So we definitely want to be able to add these two together. So our common denominator is going to be cosine x times 1 plus sine x. So we'll have to multiply our first fraction by 1 plus sine x over 1 plus sine x. In our second fraction, needs a cosine x. So that's going to give us 1 plus sine x times 1 plus sine x. We know these are going to have the same denominator, so I'm going to just combine these now, plus cosine squared x all over cosine x times 1 plus sine x. If we FOIL our 1 plus sine x times 1 plus sine x, we'll get 1 plus 2 sine x plus sine squared x plus cosine squared x, all over cosine x times 1 plus sine x. Sine squared x plus cosine squared x is 1. So we can rewrite this as 1 plus 2 sine x plus 1 all over cosine x times 1 plus sine x. So then we can say 2 plus 2 sine x over cos x times 1 plus sine x. And from here, we can factor out a 2. If we factor out a 2 from our numerator, we'll get 1 plus sine x left over, all over cos x 1 plus sine x. So now, our 1 plus sine x's will cancel, and that gives us 2 over cosine x. And we know from our reciprocal identities that 1 over cosine x is secant x. So if we hold that 2 in front, we get 2 times 1 over cosine x, or 2 times secant x, which is exactly what we were trying to get, and we've verified this expression. Next we have cosecant theta equals cotangent theta plus tangent theta over secant theta. So in this case, we're going to work with our right side of our expression, because on the left side, there's not really much we can do to get it to look like the right side. So on the right side, we know that cotangent theta is equal to cosine over sine. Tangent theta is equal to sine over cosine. And secant theta is equal to 1 over cosine. So let's rewrite all of those trig functions using what we've just identified. So cosine over sine plus sine over cosine all over 1 over cosine. In our numerator, we want to add these two together. So the only way we're going to do that is by having a common denominator. Our common denominator is going to be sine times cosine. So we'll multiply cosine over sine by cosine over cosine. And we'll multiply sine over cosine by sine over sine. So then this is going to become cosine squared theta plus sine squared theta all over cosine theta sine theta all over 1 over cosine theta. Cosine squared plus sine squared is 1 from our Pythagorean identities. And if we do our keep change flip, we have 1 over cosine theta sine theta. So we're going to keep that fraction, multiply instead of divide, and flip our cosine in the denominator to the numerator, cosine theta. Now our cosines will cancel. We're left with 1 over sine theta, and 1 over sine theta is equal to cosecant theta. That's exactly what we were looking for to verify this expression, so we verified it. Our next expression is secant x plus tangent x equals cosine x over 1 minus sine x. So in an expression like this, it's hard to see which side is going to be easier to work with. I'm going to work with the right side because we can use a conjugate to help us simplify this fraction, which can be helpful. Remember, our conjugates are whenever we have a value minus, plus or minus another value, we can multiply the conjugate, which is the opposite sign in the middle. We do this a lot when we're working with complex numbers, and we can do the same here. So if we look at our left side of our expression, we have cos x over 1 minus sine x. We can multiply top and bottom by the conjugate, which is 1 plus sine x. We're still multiplying by 1 because we're multiplying by 1 plus sine x over 1 plus sine x, but it's going to help us work with our denominator of our fraction. So this is going to become cosine x times 1 plus sine x over, when we multiply our two denominators together, this becomes a difference of squares. And so we get 1 minus sine squared x. We can rewrite 1 as cosine squared x plus sine squared x. So that's going to be cosine x times 1 plus sine x over cosine squared x plus sine squared x minus sine squared x. Our sine squared x's will cancel. So we're left with cosine x times 1 plus sine x over cosine squared x. Now our squared, we can cancel out that cosine in our numerator because we have cosine squared in our denominator. So we're left with 1 plus sine x over cosine x. Now let's break up this fraction. We have 1 over cosine x plus sine x over cosine x, which gives us secant x plus tangent x, which is exactly what we wanted to verify. And we have the same expression. And here's our last example. Secant squared x minus cosecant squared x equals tangent x minus cotangent x over sine x cosine x. So again, let's use the right side of our expression because there's more for us to simplify to give us the left side. So if we look at our numerator, we know that tangent x is equal to sine over cosine, and cotangent x is equal to cosine over sine. So we can rewrite that as sine x over cosine x minus cosine x over sine x all over sine x cosine x. Now we do want to have the same denominator so that we can combine our fractions. That's in the numerator of our fraction. So we'll multiply our left one by sine x over sine x and our right one by cosine x over cosine x. That's going to give us sine squared x minus cosine squared x all over sine x cosine x, which is all over sine x cosine x. Let's do our keep change flip. So we'll have our numerator times, we'll flip our denominator, 1 over sine x cosine x. So if we combine our denominators, we'll get on our numerator sine squared x minus cosine squared x all over sine squared x times cosine squared x. We can separate these fractions, and because we have our minus sign in our numerator, we can rewrite this as sine squared x over sine squared x cosine squared x minus cosine squared x over sine squared x cosine squared x. So now this allows us to simplify. We can simplify a sine squared x in our first fraction and a cosine squared x in our second fraction, giving us 1 over cosine squared x minus 1 over sine squared x. From our reciprocal identities, we know 1 over cosine is secant squared x, and 1 over sine is cosecant squared x. This is exactly what we saw in the left side of our expression, so we verified our identity. Thank you so much for watching. If there are any topics you'd like to see, leave them in the comments below. Make sure you're subscribed to my channel so you never miss a video. See you next time.